I just want to thank Michal and Corey and Discover and Chemical Heritage Foundation for conceiving of this event and organizing it. I want to thank the 6 distinguished panelists for coming in to share their experiences as innovators in the world of materials. And I want to thank all of you because you are what makes all of this worthwhile. Now, I've actually never been able to gather my own neighbors around my own living room to talk about materials, and so this is absolutely thrilling to me to see 200 people willingly coming here to talk about material science engineering and materials in our world. And I think we're going to have a rather engaging discussion, and I want you to be engaged as well. So at the end of this, we will have a question and answer period and a time for input, so that we really can make this a discussion of 200 and not just 6 or 7 up here. I want to begin just with a few thoughts, in a sense, to try to get us into a materials mood, if you will. And then I will introduce the speakers, the panelists. In short form, I think you have some additional biographical information in the brochure. So let me just start with a couple of thoughts. So one of the things that amazes me, well, the periodic table of the chemical elements is something that amazes me. I think of it as the mother of all pantries. Every material thing that ever was, is, or will be resides in that remarkable achievement of discovery. And so, to me, everybody in their house should have a periodic table sort of between 2 candles, in a shrine-like environment, as opposed to what most of us really hear about from our friends and neighbors, which is, oh, that thing. All right, that's the thing that made me get bad grades. I didn't get into medical school. I had terrible teachers. And that is actually that's sort of funny, but it's also a very sad thing, because it is something to revere. Now, material science is a little bit more than just the ingredients, right? It's also knowing what to do with them, how to mix and match them and rearrange them, how to heat and mix and extrude and crystallize and process them into all of the material menagerie of the constructed landscape. And we have with us 6 individuals who have been very much involved in the recent history of learning how to do that better and better. So the high-tech materials we will hear about today are testament, to this combination of working with that mother of all pantries, and then with all of the processing know-how that's been accrued over the years. A second thought. The history of technology is closely tied to innovations in materials. Historians often have found it useful to partition history according to the high-tech materials of certain times, right? So we've heard about the Stone Age, the Bronze Age, the Iron Age. Where there might have been something we call the Age of Plastics, maybe from the 30s to the 60s and 70s, before it kind of generalized into what I would almost want to call the age of materials now. And that's where the diversity of the material landscape is apparent in thousands and thousands of technologies. The innovation of striking one rock against another to get a sharp edge, something that happened probably 2 million years ago, I actually sort of look at as the original act of materials engineering. Right? This is where the expression that I don't have to be satisfied with the world as I find it, but I can transform that into something more capable and useful, and thereby make me more capable in the world. But I think it's exactly the same attitude that goes into taking silica sand and converting that into a great boule of silicon crystal. I think of them sort of as salamis that get sliced into the wafers, that get diced into the chips, that have transformed our world so much. Same attitude, the rock blade maker and the silicon crystal maker. And it's the same attitude here that I think is expressed by the members of the panel up here and all of the colleagues that they've been working with throughout the years. And then finally, the third thought before I introduce the panelists. is that innovations in materials continue to be central components of the evolution of almost all technology. Now, somehow the computer community has gotten hold of that word technology. Most of the time when you read in the newspapers technology, it has to do with computers, but we all know that materials are the flesh of virtually all technologies. So we need to generalize that word once again to think of what's behind the technologies, the materials. Materials continue to empower us more and more and provide solutions to vexing societal problems. At least this is the ideal. Among them, the need to provide the needs of a population that now exceeds 7 billion, and we need to provide for the 7 billion and the growing population from there in ways that do not deplete spaceship Earth or wreck her to the point of inhabitability. And this is an ethic that is becoming more and more central to the materials innovation mission. So let's get to the good stuff now. I want to introduce you to our 6 panelists. I will be going from my right, your left over here across, starting with Ryan Dirks. Ryan is Vice President of Research and Development of Arkema Inc. at the company's R&D Center in King of Prussia, which is not so far away. And we had a little discussion about where the name of that town comes from, and we actually did not arrive at a historically sound conclusion to that. So if somebody here knows that, come to me later and help me out with that. With the company for 20 years, Ryan has played roles of increasing responsibility in business units that include polymers, specialty chemicals, and one that specializes in plexiglass materials, which I can say is polymethylmethacrylate. Did I get that right? There we go. Short form PMMA, for those who like acronyms. He holds a PhD in solid state science from Penn State University. Next to Ryan is A.N. Sriram, Vice President of R&D for Dow Chemical Company's Advanced Materials Division in Midland, Michigan. With Dow since 2006, Sriram has been applying his company's materials products to industries ranging from automotive and sectors like infrastructure and health. One previous job was electronic technologies at DuPont, a company that also is represented here on the panel. Sriram's PhD is in ceramics from one of the cathedrals of materials and engineering, the Massachusetts Institute of Technology, which had one of the very first departments that you would call material science and engineering. I think founded somewhere around 1959, 1960. Next to Sriram, we have Tom Connolly, Executive Vice President and Chief Innovation Officer of DuPont. Starting at the company's experimental research station in Wilmington, Delaware in 1977 as a research engineer, Tom has held positions of leadership for several of his company's businesses, among them Kevlar and Teflon, names we know and are very familiar with, while stationed in the US and around the world. He now is responsible for 3 major business units, for science and technology outside of the US, and for something called integrated operations. Which, as far as that kind of confuses me, but I think it means he's responsible for just about everything it takes to get products made. Tom earned his PhD as a Winston Churchill Scholar at the University of Cambridge. Next to Tom is Greg Nelson, Senior Vice President and Chief Technology Officer of Eastman Chemical Company, headquartered in Kingsport, Tennessee. In his earlier years at the company, beginning in 1988, Greg did research in the chemistry and processing of polymers, as well as in laboratory automation. In 2006, he became Vice President of the Polymers Technology Division before continuing on his way to his present position. Greg's PhD is in analytical chemistry, which he earned at Emory University, and he added an advanced management credential from Harvard in 2007. 2 more. Next to Tom is Greg Nelson. Vice President and Chief Technology, is Mark Derisky. I don't want to introduce you twice because then you'll double responsibility, and that's not right. Mark Derisky. Mark is the Global Intermediates Technology Manager for ExxonMobil Chemical Company in Houston. He joined the company at its Baton Rouge chemical plant shortly after earning his bachelor's degree in chemical engineering from Tulane University in 1986. In 1997, he moved to the Basic Chemicals Division, where he had to worry about the company's propylene and ethylene businesses. which provide basic feedstocks to the makers of hundreds of polymer-based materials and thousands of products based on those. In the last decade, Mark held several high-level managerial positions before taking on his present role. And our sixth panelist today is Chris Pappas. Chris is president of and CEO of Sriram, a company specializing in polymers, emulsions, and rubber materials. Spun off from Dow in 2010, the company now is part of Bain Capital Partners' portfolio. With presence in over 30 locations around the world, the company is headquartered in nearby Berwyn, Pennsylvania, which is just south, I think, of Ryan's home base, and just to the west of us here. Chris started his career at Dow before moving to DuPont in 1996, where he began an upward managerial trajectory. And in the last decade, he was with Nova Chemicals Corporation, becoming its president and CEO in 2009, before taking on his new leadership position with Sriram 2 years ago. So you can see we have 6 distinguished panelists who have had their fingers in materials innovation in many ways and for many years. So I'm going to now move over here, and there will be 3 sort of thematic questions that we'll be working with here, and each one we'll try to spend about 15 or 20 minutes with, and then I'll open up the floor to questions. And I do hope that as we go, that you mark things down that interest you, and that you really do become engaged in the conversation that we're about to have. So I'd like to start, in a sense, from a somewhat historical perspective, and then we'll be moving toward really the future of materials. So, you know, the one thing I want to say about the materials as a story and as storytelling is that most people look at materials as a means to an end, right? So people think about their tires and their computers, but they don't really think so much about the elastomers and the semiconductor materials that are in those products. So it's always been a sort of a difficult story to tell, as opposed to something like, you know, medicine, where you have instantly life and death stories. There's tension, and tension is the currency of the storyteller. So it takes a lot to really get the good stories of materials out there and to find the human elements in there. The question I'm asking here, though, is what roles have materials innovations played in the recent history of technology? And to put a framework around that, in some ways, we could go back to the World War II era, when materials innovations, I think, became, you know, obviously important to a lot of people. One example, when the supplies of natural rubber, for example, were cut off, and so if you don't have rubber, you don't have tires, you don't have a war machine. So it was absolutely a critical thing for the Allies to find a way to develop synthetic rubber. So we can start there, but I invite all of you to think of recent history as just in the recent decades and years, and feel free to draw on illustrations from your own work and your colleagues' work at your companies if that is helpful. I'm also going to sort of run this like a Quaker meeting, so I'm asking them to speak as they are moved. The question, as opposed to going serially like this. So the question has been asked, and who would like to start? Oh, there's competition. Sriram.
Okay. Well, thank you for your question, Ivan. You know, you mentioned computers. Materials are really central to our modern way of life. I would say even critical. So the easy answer is look at our personal electronics, right? Whether it's a smartphone or iPad or tablets, and then you go home and your computers and flat panel displays. That's obvious to almost anyone and be held in awe of the materials that go in there. But I think what is critically important for us to survive and our well-being is something more fundamental, like water, food, energy, shelter. And this is where materials have made just as aggressive and creative innovations like in the computers. So let me begin with water. You know, you've heard of the old phrase, water, water everywhere, not a drop to drink, for folks lost at sea and so forth. But I beg to differ that in the last couple of decades or so, we have been able to enhance, how do you economically take the salt water from sea or brackish water from deep underground and make it very high quality potable water. So barely 20, 25 years ago, it took 16, 18 kilowatt hours to take that water and get all the salt out and other ingredients out. Now we can do this commercially for about 2 kilowatt hours. So that's an 8-fold increase in barely a couple of decades. Think of Moore's law in there, and it's not that far off from aggressive innovation, if you want to think of it like that. Sydney has 15% of its water through reverse osmosis, and playing on something Ivan said, what Dow has done or our companies and colleagues have done is able to reduce that energy content. Energy is money and we are quickly beginning to realize that, right? So, and what our company, my company, is committed to is by 2015 we'll further reduce that by a third. So that's significant reduction in the cost of available pure water. And as our society develops and populations increase, it's going to serve our critical need. You think of food, think of how food is preserved. A pound of beef lost is same as burning a little over a gallon of gasoline from a CO2 footprint point of view. So it was canning, late 1800s or so, if you want to go back that much. Think of an 18-wheeler, hauling about 25,000 cans of food. How much weight it has to carry, right? A lot of, whether they're using diesel or some other liquid fuel to do that. Now we have a multi-layered, highly engineered barrier layer. It has plastics of various kinds, maybe for higher end, even a metallized plastic layer, adhesives and so forth. And it reduces the cost of transportation, the energy footprint of transportation, and extends the shelf life. You had to freeze meats if you want to preserve for a long period of time. Now you can go between various parts of supply chain in these kinds of materials technology and save a lot of energy, a lot of money to our pockets, and so forth. Moving to shelters now. Okay, so 48% of the entire energy footprint of the US is spent in keeping our living spaces comfortable, well lit, well heated during winters, and well cool during summertime. And this is entire energy footprint. This is production of every product, agriculture, driving, transportation. So if we save, we have to conserve that energy. So if you insulate your houses well, you can think, the biggest component of where the energy footprint is for the nation, you can save a lot. We have several products, insulation blue boards and great stuff. You may have found this in a hardware store to seal your windowsills and prevent leakage of energy from your house. So if you look at what it takes to survive and for our well-being, material science has made as aggressive an innovation as in any other industry.
Tom, I know your hand was up.
Yeah, let me start by, in a very unquakerly fashion, push back on the notion that materials aren't exciting. And maybe we're the outliers on this panel up here, and hopefully we have a few kindred spirits out in the audience, but we're the guys who really think materials are exciting, and we don't need more of a story than just the exciting materials themselves.
This is a self-selected audience.
Now I will go on to say that I know you're interested in stuff, and I'd start out by saying the world has enough stuff by and large. All right, we don't need more stuff, and I think many of the companies we represent here today in the past, we're always concerned about the volume side of the equation. So we find an application that required a lot of stuff, and it looked good to us. And I think where the world is going now is the world has enough stuff. It needs smarter stuff. It needs higher performing stuff. It needs more renewable or greener stuff. It just doesn't need more stuff. So we got to be looking at the value side of the equation, not just the volume side of the equation when we talk about materials. Sriram's covered a lot of interesting subjects. Maybe I'll talk about something that we know something about in the area of alternative energy and photovoltaics. And you go back to the 1880s when the photoelectric effect was first discovered, and it took about about 120 years for the total installed base of PV to reach 1 gigawatt. That was in the year 2000. Last year, the world installed somewhere between 10 and 13 gigawatts in a single year. So this thing has really taken off, and it's been enabled by the materials. Part of it is those ingots of those salamis of silicon metal, right? That we heard about a little bit earlier today. But part of it is a suite of other materials that allow us to harvest the electrons off the surface of that silicon wafer and turn it into electricity far cheaper than we could even a decade ago. And I know my own company has a suite of materials offerings that improve the efficiency, extend the lifetime, and flat out reduce the cost, the cost in use of those solar modules that are showing up literally everywhere. And we're just now approaching that point of grid parity where the cost of generating from solar is equivalent to the cost of the fossil alternatives. And when we cross that point, believe me, that growth rate, which has been spectacular, is even going to accelerate further.
Okay. And I just want to remind people, now that you reminded me of the beautiful crystals that are right across here. So I suggest that anybody, when they come back here, to go over to the museum and really just see how beautiful these materials are. And that's just another aspect I want to bring up for me, why it's been such a pleasure to write about materials, is because they really are stunning objects in the world. So when you look at the crystals across there, that's another way of looking at them purely from their sort of aesthetic aspects and potential. And artists, incidentally, we'll get to this later perhaps, are beginning to use advanced materials so that they're beginning to take, not so much of a technology approach to new materials, but really looking at them for their aesthetic potentials as well. But I get off track. Any other input on this question of what roles materials innovations have played in recent history?
Let me mention one thing to pick up on what Tom said. People think of innovation all the time as brand new things, and they don't always think about innovating with materials that have been around for a long time. If you take basic molecules like styrene monomer and butadiene, and if you arrange them in the right way, and if you apply them to a very basic application like an automobile tire, and I'm sure all of you in here have a car and have automobile tires, and connect the technology of today with molecules that are that old and rubber technology, and put functionalization in the right place on those monomers and polymers, and construct a compound in combination with silica and carbon black, where you can change the hysteresis, the actual physical recovery of the rubber itself, in a way that the tire has better rolling capabilities, no loss of wear, and no loss of wet grip, which are three of the most important properties in a tire. If you can do that with materials that have been around for 70, 80 years, but do it in a creative way, you can create tires, which companies that work with our company are now doing, that can improve gas mileage by up to 10% in a vehicle, just by changing the tires. Now, this technology has been available in what companies today call high-performance tires, really for just the last 3 to 5 years. But it's been available built off of molecules and rubber compounds that had been around for 50, 70 years. So in, I think, all of our companies, what we try and do is look for places in the marketplace where you can make the connection between something that's really valuable, in this case, better gas mileage, without sacrificing wear or wet grip, a tire that still grips in the rain, doesn't wear out. And if you can provide better rolling resistance, you can have a tire that, of course, is highly advantaged. And that's a great example, I think, building on what Tom said, where you don't have to go back to basics. You can take basic technology and really innovate around basic technology. And when you do stuff two, which I know you will do at some point, a theme to think about, I think, is not just brand new things, but using technology that's been around in a very innovative way to solve today's problems.